Hello, welcome to the section 1.6 pre-class video assignment. In this section, we're going to talk a little bit about the existence and uniqueness of solutions for nonlinear differential equations. Basically, the idea here is that a lot of nonlinear differential equations are actually very difficult or even impossible to solve. And we're basically stuck with trying to use numerical methods. Again, we started talking a little bit about numerical methods in section 1.3. There are lots of other numerical methods we didn't actually get to and we won't be talking about, but there are these methods to solve or approximate solutions to an initial value problem. But what is very useful then in such a situation when you're trying to approximate is understanding whether or not it is reasonable to expect a solution to exist, and if it does exist, whether the solution is unique. So we're already talking about the solution to an initial value problem. Under what conditions will it exist, and under what conditions will it be unique? So we're going to start here with a little demonstration exercise here. Here's a fairly simple differential equation. dy dx equals 3y to the 2/3. The initial condition is y of 2 equals 0. So we're basically looking for the particular solution curve to this dE that passes through the point 2, 0. All right, so the exercise is then, okay, first, in the first bullet point here, we're to show that the function y1 equals 0. So the constant function y1 equals 0, can we show that this is a particular solution to this initial value problem? So there's two things to check here. Does this constant function solve the dE, and does it satisfy the initial condition? So this is a fairly trivial solution. In fact, if the function is y1 equals 0, the derivative y1 prime is also 0. And if we plug in our functions, we put in 0 equals 3 times 0 to the 2/3. That is, of course, 0 equals 0. That is an identity. So yes, this function does satisfy the differential equation. Furthermore, if we look at the initial condition, if the function is constantly equal to 0, then the function is also equal to 0 when x equals 2. So it does, in fact, solve the initial condition as well. So, in fact, the curve y1 equals 0 is in fact a solution to our initial value problem, and I went ahead and graphed it in green right here. This is our solution curve, y1 equals 0. It's basically just the x-axis, right? The x-axis is a curve that solves this dE and passes through our condition point at 2, 0. All right, so second bullet point here is, does the function y2 equal x minus 2 all cubed? Is this a particular solution to the same initial value problem? So we can check. This is less trivial, but not too difficult. We will need to get y2 prime. So if the 3 comes down in front, x minus 2 squared, this would be our derivative. So if we plug in our derivative on the left-hand side and the function on the right-hand side, we indeed get an identity here. Basically, we get on the right-hand side 3 times x minus 2 cubed to the 2/3. Here we multiply exponents. 2/3 times 3 is 2. So we do get an identity here. So this function does solve the differential equation. Also, we can check, does it satisfy the initial condition? If we put x equals 2 into the original function, we indeed get 0. So here is another solution to this particular initial value problem. We might note, for graphing purposes, y2 is a cubic function that has been slid over horizontally 2 units. So I went and plotted this one in red. Here is our second solution to this initial value problem. It is, again, another curve that satisfies the dE and also passes through the requested initial condition point. So here I have an example where we have an initial value problem. It does have a solution. So the initial value problem does have existence of a solution, but that solution is not unique because we have identified two solutions at least so far, right? So this one has a solution, but is not unique. So this is the sort of thing we'd like to be able to identify ahead of time. Can we decide when the solution will exist? Can we decide when the solution would be unique? Again, having a unique solution is valuable in terms of solving a DE using a difficult DE, solving it using numerical methods. It's nice to know that what you're trying to estimate actually exists. So this is important. So we're going to talk a little bit here about the theorem of existence of uniqueness. The theorem is actually very difficult to prove. You will not find it in the proof in a textbook at this level, but we will talk about some of the ideas here. But we will need to talk about a couple of things. So it turns out that, we will come back to this, but it turns out that we are interested in this function f of xy, as we saw back in section 1.3, and the nature of this function basically determines whether we have a solution and whether it is a unique or not. And it comes down to two things: the continuity of f of xy and the continuity of the partial derivative of f of xy. So these are a couple of things we want to talk about before we come back to this theorem. So let's take a look here. So first thing I would like to just point out to you, just to have a picture in your head, what does it look like when you're talking about domain of a function of two variables? So a function of two variables means there are now two input variables and one output. So this could be an expression involving x and y. We put in a value for x and put in a value for y, and we get a single output z. So this is like, and we saw this when we did direction fields and slope fields, that it's kind of like putting in an XY pair, putting in a coordinate pair into our function. And of course, there are conditions under which the pair may or may not work. The coordinate pairs for x and y that work and give a well-defined output z are called the domain. So as a little picture in your mind, we are talking about picking coordinate pairs, plugging them into a function and getting an output. Again, that means the coordinate pairs, the ones we can pick from the plane, basically correspond to the domain. And so the domain of a function of two variables really represents a region in the xy plane. So rather than just being an interval of x, as we were accustomed to in Calc 1, this is now a region in the xy plane. That is probably the big idea here that is helpful to keep in mind, that when we're talking about the domain of such a function, it is something we can represent by a region in the xy plane. And again, you can imagine taking a point, something like x0, y0, and plugging it into our function, and we would plug it in, and we would plug it into our function, and we would get an output here. This would be z0, let's call it, of f of x0, y0. So we can kind of picture this as a sort of three-dimensional input-output for a function. So this is kind of the situation we are dealing with, and we will want to, and we will have the need to display and think about domain in terms of a region in the XY plane. So here's some little discussion of that. Again, as we will see in this theorem, the existence and uniqueness of the solution to a first order initial value problem ultimately depends on the continuity of a function f of xy, and also the continuity of something called its partial derivative. We would call this del f del y. So we will talk more about partial derivatives here a little bit later. But again, we were looking for the continuity of a function of two variables. So a little fact that continues from functions of a single variable. Maybe you remember this from Calc 1. As for functions of a single variable, if we're dealing with non-piecewise and hence non-absolute value type functions, and we want to know the continuity of such a thing, it turns out that non-piecewise, non-absolute value type functions are continuous on their own domain. So when we are interested in the continuity of f of xy, what we really can do is think about the domain of f of xy. The domain of f of xy is where f of xy is continuous. So that is kind of why I'm talking about this domain issue. So the good news then is conceptually, everything else is as we remember it from Calc 1. There are only two mathematical restrictions to the domain, and that is you cannot divide by 0. So if in your function you have 1 divided by something, that thing in the denominator cannot be 0. If for a function you have the square root or potentially any even root of something involving x and y, the thing you are taking the square root or even root of must be positive or 0. It can be 0. Square root of 0 is okay. So solving these ultimately come down to inequalities. They turn out to be inequalities that turn out to effectively be something we can graph as regions in the XY plane. So this is something we are going to be interested in, being able to graph graph such a thing. All right, so then briefly, let me go back to some of the other little topic we need to talk about, and that is partial differentiation. If you have already seen Calc 3, then you should be familiar with partial derivatives. Calc 3 is actually not a prerequisite for our course, so you might not have seen this yet. It's not very difficult, but again, a little bit of Calc 3 knowledge is worth reviewing here. So a little background here. In Calc 1 and Calc 2, we've been working with functions of a single variable only, y equals f of x. For a function y equals f of x, we were able to talk about what's the derivative. Basically, we're saying, how does y change when you change x, right? Remember, a derivative is an instantaneous rate of change. So the derivative of y equals f of x is what is the instantaneous rate of change of y as x changes. We now at times in our work here in differential equations, we are interested now in a function of two variables, z equals f of xy. So what does it mean to talk about the derivative of such a thing? And the answer is, it depends. There is more than one derivative. So the idea again is, a derivative is the rate of change of the output as the input changes. Here, we can have different inputs changing. So the classic partial derivatives are, what is the rate of change of the output z as x changes, but y remains constant? Similarly, we can also talk about what is the rate of change of the output z as y changes, but x remains constant. These are called the partial derivatives of f of xy. So there is not just a derivative, we have multiple partial derivatives in this case. So to denote partial derivative, we write them this way. So we have, this is a Greek letter delta here, or actually it's a symbol that looks a little bit like a Greek letter delta. We read this as saying del f del x. Instead of df dx, we say del f del x, del z del x, del f del y, and so on. So that's what we'll be interested in here. So for the purposes of what we need it, we are interested in del f del y. Del f del y is the rate of change of the function's output as we change y, but keep x fixed as a constant. So we are actually interested in this one for our purposes in this section, del f del y. Now, how do we find del f del y? This is actually quite easy. If you can differentiate, you can find partial derivatives. The idea is to find del f del y, just remember that we're considering y being the thing that is variable and x is the thing that is fixed or constant. So you basically take your function f of xy and you differentiate it as if y was the variable and the x is a constant. So a couple of examples here. What is the partial derivative with respect to y of the function 3xy to the 4? So this is not a difficult one. We treat 3x like it's a constant. So what is the derivative of y to the 4 with respect to y? Well, we would take the 4 down in front and then reduce the exponent by 1. So the 4 comes down in front and gives us 12x in front, and then y cubed is what's remaining. So that is the partial derivative with respect to y. You just pretend like x is a constant and y is a variable. This one is also pretty easy. What is the derivative with respect to y of 3x cubed plus x squared y? Well, 3x cubed is basically just a constant with respect to y. So when you take the derivative of a constant, it becomes 0. And then what is the derivative of a constant times y with respect to y? Well, that is just the constant. So this is our result. The derivative is just x squared. Last but not least, and this will be relevant to our exercise that we were talking through, that is the partial derivative of a function of y only. So del y of a function of y only is no different than taking the derivative with respect to y. So del y of 2y cubed is dy of 2y cubed, which of course is 6y squared. So that is a particularly easy case, but again, not always the case here. And again, what we are interested in is for this section is being able to find del f, del y, as we shall see with this theorem. First, here's a couple of little examples for trying to find some simpler partial derivatives with respect to y. So give that a go. And then there's a second example try as well. Okay, so let's go back to our notes then, our theorem here. So I'm going to head back to that theorem we were talking about that tells us about existence and uniqueness. So this is what the theorem tells us. Consider an initial value problem. So we have a first order DE equals, so y prime equals f of xy, and we have a initial condition point, namely x0, y0. Right, this is our initial condition point. So the theorem states, suppose we have this open rectangle of some sort. Inside the open rectangle is our initial condition point. So if the function f of xy is continuous on the rectangle R, then this tells us there exists at least one solution to the initial value problem on some open subinterval of AB. So inside the rectangle, on the X interval, there would be some interval where we have at least one solution. So it turns out that the continuity of f of xy tells us about existence of a solution. Then similarly, the second part of this theorem says if the partial derivative del f del y is continuous on this open rectangle, then we have a unique solution to the initial value problem on some open subinterval that contains x0. Exactly how big this open subinterval is not given to us by the theorem, but we know it is an open interval. So there is some interval that contains x0 where we have a unique solution in this case. So the continuity of the partial derivative tells us about the uniqueness of our solution. So let's take a quick look here at this example we were working on. We worked on this simple example and actually found that we did have solutions. We had two of them. So we have two solutions to this initial value problem. Hence, we have existence, but not uniqueness. So let's see what that looks like. Apparently, this example we have up here must violate this existence and uniqueness theorem because it is not showing us uniqueness. So if we take a look, this was the initial value problem. If we look at the function f of xy, this is what we have, yes? The function f of xy has no domain issues. If we ask ourselves, where is this continuous? It is continuous on its domain, and its domain is all real numbers for y. Again, there are no x's here, so this is all xy pairs work for this function f of xy. Hence, we know there is a solution, and we saw there was a solution, so that is correct, yes? Then the other thing we want to check for uniqueness is we want to check the partial derivative of 3y to the 2/3. So again, this being just a function of y, the partial derivative here is just the derivative with respect to y. So 2/3 comes down in front, times 3 is 2. And then we have a y to the minus 1/3. That is our partial derivative. More suggestively, I can write it like this. It is 2 divided by x over y to the 1/3. Now, for this one, where is this continuous? It is continuous on its domain. This one will have a domain problem when y equals 0, so it is continuous as long as y is not equal to 0. So let's see what we had. This was our initial condition. Our initial condition happened to be a place where y equals 0. This was not allowed for uniqueness. Hence, this is why we had the possibility, and in fact saw, that we had two different solutions to the initial value problem. This particular example does satisfy the existence part of the theorem, but it fails the uniqueness part of the theorem, and hence we cannot assume uniqueness, and in fact it did not have uniqueness here. Another way to look at this, and kind of what we want to be looking at eventually here, is I'm basically looking at this partial derivative and asking myself, what is okay here? And it turns out that I can pretty much have an initial condition for this particular initial value problem. I can have an initial condition anywhere except on the x-axis, anywhere where y equals 0. So I could have taken an initial condition up here. I could have taken one over here. Could have taken initial conditions. The only place I couldn't have an initial condition was on the line y equals x. So we can kind of shade in the domain here, or the region where we have a unique solution that exists. It is everywhere in the plane except for the x-axis. The x-axis is the only place where this is. So here, y cannot be equal to 0. That is not part of our, cannot be part of our initial value problem. So that's a fairly simple example. You're going to see, again, some necessity here in this section to be able to, like we did here in a fairly simple case, think through what is the domain of something like this? What is the domain of something like this? Here are a couple of examples. Okay, in the second one here, you'll actually use the graphing feature to draw your domain. So try that. Okay, so otherwise, let's go back to the prerequisites page here. This is what we were looking at. So we did talk a little bit about partial derivatives. I had you do a couple of easy ones earlier. There are some more tricky ones. Again, they just look confusing. Just remember, when you're doing a partial derivative, you are in fact just differentiating with respect to the respect variable, the one on the bottom, and treating the other variable as if it were a constant. So there's a couple more to try for practice. These are ones that are pertinent to the rest of our section, so give them a try. Okay, and then here's the second one to try. All right, so that's some partial derivatives for practice. Again, we also are talking about the domain of functions like this. So there's a couple more to try for finding the domain, slightly more complicated, but again, not actually all that difficult to try them out. Okay, and then a second one to try. All right, so one more thing I want to talk about before we end this video. Something we're going to talk about towards the end of the section, and that is we're going to run into something that are called integral defined functions. So the idea here is, despite everything we've learned in Calculus 1, Calc 2, there are still functions that we cannot integrate by hand. Even things that don't look all that complicated, cosine of x squared, e to the power of x squared, e to the x squared. None of these are actually integrable by hand. Now, when I say that, what we really mean here is we're not saying that the integral doesn't exist. We are only saying that their antiderivative functions cannot be represented in terms of the elementary algebra and trig functions that we're familiar with. We don't have any way of writing them down. So when this happens, when we need to refer to the integral of a function that we can't integrate, we do it by referring to it as an integral defined function. So for example, how can we refer to the general antiderivative or the general integral of cosine of x squared? We can refer to it like this. That is, we write it as the integral from anything, any point A, to the variable x cosine t squared dt. A little note here about notation. The variable, the input for this function, if we were going to give this function a name like g of x, and then this would be big G of x, the x in the upper end of the upper limit of the integral, that is actually the input of this function. We then, again, have a variable here, t squared t dt. We would consider this just a dummy variable. We're accustomed to calling this x, but I don't really want to call this x because I've already used x as the input variable in the upper limit here. So typically we would change this name here to t squared dt. Now, this seems a little complicated or seems a little confusing. Don't overthink it. It is much easier than it seems. This is pretty much a good justification of what we're doing here. And that is, if I take the derivative of this integral defined function, if I take the derivative of this integral defined function, what do I get? Well, we already decided that this guy in here is the antiderivative of cosine of x squared. So when I take the derivative, I ought to get cosine of x squared back again. So that should make sense, right? If I do the derivative of the antiderivative of cosine x squared, I should get x squared back again. Now, that should look familiar from Calc 1. This is just the fundamental theorem of calculus. If you take the derivative of a function that looks like this, what we did is we take this x and we put it in for t, and this is our answer. So this works, right? This is a way we can, if we don't have a way of writing down this antiderivative explicitly using functions, we can write it in this fashion. So basically that is the idea here. Here's a little MyOpenMath question about that. Again, don't overthink it. There's a two-part question here. You are to evaluate one of these functions. So if I give you if I ask you if this is g of x and I ask you to evaluate g of 1, I'm basically telling you to put a 1 in the upper limit of the integral and evaluate. So in order to evaluate, since you don't know how to integrate by hand, this would be something you can integrate using technology. And then there's a little question, just remembering how to do this. What is the derivative of an integral like this? What happens here? Don't overthink it. It's fairly straightforward. And that's it for the video today. We will finish up this packet together in class. Thank you very much.